Primary that originates from an explosive ignition of hydrogen burning on the surface of a white dwarf. In the course of these outbursts, the hydrogen of the ingested gas thus fuses until the white dwarf has enriched its core with enormous amounts of contaminated carbon. Further combustion and accretion processes cause the stellar core, which now resembles an oversized diamond, to become steadily more unstable. Once the limiting mass is reached, the entire carbon supply is burned to nickel and iron within fractions of a second, which means that it detonates as a Type 1a supernova. Unlike a core collapse supernova, however, no compact object such as a neutron star or stellar black hole remains. The matter of the dying white dwarf is completely catapulted into the gigantic expanses of space. Also, the companion star is not unaffected by this primordial event. It transforms into a so-called runaway star due to the high orbital velocity with which it once orbited the white dwarf before it literally flies away. Violent nova eruption. Now that we have taken a look at the two best known basic types of supernovae, it's time to take a look at an exciting discovery that researchers made just a short time ago. In detail, the researchers were dealing with the precursor of a Type 1a supernova. The system that became the focus of scientific interest is called RS Ophiuchi, as the researchers from the Max Planck Institute in Munich discovered during their investigation. The nova outbursts were accompanied by an unusually intense emission of gamma rays. About 5,000 light-years from our blue home planet, a white dwarf in the eponymous constellation Ophiuchus incessantly accretes material from its companion, a red giant star. As briefly described earlier, the absorption of hydrogen gas on the surface of the white dwarf sometimes leads to overheating that sets off violent thermonuclear explosions. These violent events usually follow a fixed cycle. In the case of RS Ophiuchi, about 15 years elapsed between nova eruptions. Finally, the most recent nova observed by experts was accompanied by an unexpectedly high gamma ray burst. In detail, the emission, which was registered and analyzed with the help of the two magic telescopes on the Canary Islands, reached an incredible value of 250 giga-electron-volts. This is one of the most intense gamma ray bursts ever observed by astronomers. The explosion produced shock waves that accelerated particles to near the speed of light. Based on their collected data, the scientists concluded that the gamma rays originate in energetic protons, the nuclei of hydrogen atoms. In other words, nova eruptions are also sources of cosmic rays. This means a high-energy particle radiation, which is mainly composed of protons, but also of electrons and completely ionized atoms. The corresponding particles move through the gigantic expanses of the cosmos at almost the speed of light. Compared to the enormous shock fronts generated by supernovae, however, the forces released by nova outbursts are significantly less intense. One day, RS Ophiuchi will also be torn apart as part of a Type 1a supernova. However, a look at the experts' next discovery shows that not all objects want to follow the supposedly fixed rules of the cosmos. Stellar death throes. When a massive star goes supernova, it shines brighter than full-grown galaxies for a few days, before rapidly losing luminosity afterwards, a supposedly fixed scheme, which went completely ad absurdum. In the case of the object IPFT-14HLS, astronomers like Stan Woosley, who dedicated themselves to the investigation of the structure, called this simply bizarre. The background? It seems as if the star in question simply does not want to die. Originally discovered in September 2014, the stellar explosion was initially thought to be a perfectly ordinary supernova. However, when an attentive intern sifted through the collected data, again 5 months later, he came across a puzzling detail. The supernova first became fainter, as expected, only then to shine brighter again afterwards. Even more puzzling is the fact that this was not a one-time phenomenon, but a reoccurring one. Over an observation period of 2 years, this interplay of dimming and intensification was registered 5 times. The analysis of the light spectrum paints a clear picture and perfectly matches the basic characteristics of supernovae, ruling out any other event. Never before have experts been confronted with a supernova lasting years. Normally, dying stars go out completely after about 3 months. But that's not all. A review of archival images showed that another stellar explosion had occurred at exactly the same location in 1954, but had been overlooked at the time. The question of what is behind this supernova hiccup is still the subject of research. Now we want your opinion. What do you think about the stellar explosion spectacles that regularly occur in the cosmos? Drop us your thoughts, suggestions, and feedback on today's video in the comments below. Still in the mood for more exciting contributions on the topic of outer space? Then take a look at the other videos on our channel, which we have linked for you here in the credits. Thanks for your interest. Take care, and we'll see you next time.
The James Webb Space Telescope is on a mission to unlock the secrets of the cosmos.
Think about it as a telescope that enables us to see the hidden universe.
Searching for the chemical building blocks of life beyond Earth.
Is there life on an Earth-like planet around a sun-like star? Is there an Earth 2.0 out there?
Hunting for clues to unravel the mystery of black holes.
Where do they start growing? How bright do they get?
And probing deeper into our cosmic history than ever before.
We are reaching back to what we think is the first epoch of galaxies. And we've only just started. That's the craziest thing, right?
New Eye on the Universe. Right now on Nova.
This telescope was designed to answer some of the biggest questions in astronomy today. Everything from detecting the very first galaxies that were born after the Big Bang, to looking at objects within our own solar system, and everything in space and time in between.
We're trying to tell the whole human story from the beginning of the Big Bang right up to did life emerge on another Earth-like planet around another star like our sun? And that's a massive story.
But I'm also, got my ears pricked up for what are we going to learn that we didn't even know we were supposed to be looking
for. The James Webb Space Telescope, also known as JWST, is the largest, most complex space telescope ever built. Plagued with mishaps and cost overruns, it was decades in the making.
We got to the point where we started thinking, is this thing ever going to fly? Right? Is it too complicated?
It was finally launched on December 25th, 2021.
This will be humanity's last view of the James Webb Space Telescope as it moves to its workplace about 1 million miles away from Earth.
JWST is an example of what people can do on a large scale. 20,000 people around the world contributed to making this telescope exist.
Now, researchers are taking their new telescope on a test drive.
Method's always been a mystery. This is like our new souped up convertible that we want to take out for many spins, multiple spins, and really test its limits.
Just look at that.
There's a period where you have to feel it out. You've got to learn how to use it. And that's what we're doing.
We had some idea what we might be going to see in this galaxy.
So we're trying to really get up to speed so that we're not just driving the car, but we're really learning how do you take the corners the best? How do we optimize what we're doing here?
This is a story of the ups and downs of exploring the cosmos with a brand new telescope.
We're kind of guinea pigs to show how this all works. Took me a while to figure it out, but
pushing it to its limits.
so this is on the surface.
In its very first chapter of exploration, researchers are finding out what their new eye on the universe can reveal. On July 12th, 2022, the world finally got a look at JWST's first images.
I was flabbergasted, right? It was better than I could have imagined. I knew they were going to be good, but I didn't think they were going to be that good.
The thing that struck me was the amount of detail we were seeing in these images.
It's sort of like putting glasses on for the first time. You know, everything is just like crystal clear, and there's just so much to see.
I guess my reaction was just a total sense of wonderment. You know, it's like sort of that feeling when you were a kid and you look up at the night sky and you just look out into the universe and you see all these stars and you wonder how big is the universe and when did it all start? I felt that looking at those images. I just felt that sense of wonderment.
As the first batches of data and images pour in, scientists are hunting for new clues to some of our most profound questions.
I study galaxies in my own research, and so I am really excited to see what that first epoch of galaxies to form after the Big Bang, to see what those galaxies are like. But if I'm being honest, I think the most important question we have in astronomy, or maybe even as a species, is there life out there?
Are we alone? It's definitely one of the key questions that I would love to answer.
For me, that is such an earthly shadow that by itself would be worth the entire telescope.
There are over 5,000 exoplanets that have been discovered so far. The actual number changes every day, so even I can't keep track.
Exoplanets are alien worlds.
Oh my God, we're gonna.
I
know.
It really does blow the mind when you think about Carl Sagan.
Look at that.
Billions of galaxies.
It's over there.
So that begs the question, you know, are there trillions of exoplanets?
Who lives in the snow?
You gonna go
To
outside?
put this in perspective,
What about?
our galaxy,
Yeah.
the
Too cold.
Milky Way, contains at least 100 billion
If I don't go,
and astronomers estimate
you know,
it may be
I need to
home
move.
thousands of solar
Fresh air.
systems with planets
But I need boots, not these.
The big question is, can any of them contain life?
The odds that one of these planets
Poor
has
Cash, he's all by
life
himself.
are very high.
Are we alone in the universe, right? All common sense of looking at how biology, chemistry, geology, and physics work would say no, we're not alone.
Over the last few decades, our most powerful telescopes have been on the hunt for life as we know it. But just finding these distant worlds is a monumental task.
As we're looking at planets within our galaxy, outside of the solar system, the first thing we need to remember is they're really, really small.
They're also light years away and hidden by the glare of the star they orbit.
You can imagine, it's really hard to find something faint in the glare of that really bright star.
I often heard detecting exoplanets is like looking for a firefly in front of a lighthouse. But I might argue that it's actually more challenging.
So astronomers have been very creative and they have come up with techniques that basically look at the planet when they pass in front of the star.
So just waiting patiently, looking at the stars, such that you see a little dimming in the light because the planet blocks a little bit of that light.
The tiniest dip in light can reveal the presence of a planet. And as starlight passes through the planet's atmosphere, JWST's instruments search for chemical clues to what this alien world is made of.
There are two types of scientists from this agenda. Cameras.
Hi! Hello po! Shout out!
That produce spectral rainbows. And the public is always fascinated and awed by the images that come. And these images
Yachaka! Hello! Yachaka?
But arguably, arguably
Shout
the
out.
first of scientific instruments is the spectroscope.
To demonstrate
Yeah,
what a
check out.
spectroscope reveals, Matthew Diaz built a tabletop version while he was a JWST intern. He uses a flashlight to simulate the light of a celestial object. The light passes through a lens, a lot like the lens of an old-fashioned camera.
And it focuses all the light to one point. There's this little slit here that allows the light to pass through.
Next, the light passes through another lens, and then through a prism.
What the prism's doing is it's splitting the light into colors, and that is how you get your spectrum.
It's the same as if you see a rainbow. The light is actually being broken apart in such a way that you can see distinct colors.
And this spectrum of light is chock full of information.
Each molecule has their own fingerprint, just like you have a fingerprint, like I have a fingerprint that's distinguishable. So we're looking for these key fingerprints of different molecules.
What distinguishes one spectrum from another are gaps where atoms and molecules reveal their identities by absorbing light.
Molecules in space, on stars, in planets, can absorb certain colors of light. They just take that light out of the rainbow.
So you look for the pattern of lines and say, that's the barcode of calcium. That's the barcode of sodium.
They're fingerprints. They're like little signs with a little placard saying, hello, I'm hydrogen. Hi, I'm oxygen.
JWST spectroscopes are specially designed to detect these fingerprints in the infrared part of the spectrum.
So this is where we have signatures of key molecules that we want to look at in space, like water, carbon monoxide, carbon dioxide, methane. These are really key ingredients, essential for a habitable world, or what we would associate with life.
Exoplanet researchers start their search for these key ingredients by exploring the atmosphere of a gas giant 700 light years away. WASP 39b is bigger than Jupiter and vastly bigger than Earth.
It's larger than Jupiter, but it's a lot less dense than Jupiter.
That makes its atmosphere bigger, puffier, and easier to detect.
We had studied WASP-39 with the Hubble Space Telescope. We had detected water vapor in its atmosphere already. And so we wanted to study this planet at new wavelengths using new instruments with a new telescope to see if we could get a bigger, broader picture of the planet.
Their goal? To find out if Webb spectroscopes can detect a molecule that's never been detected in an exoplanet's atmosphere. One that is critical for life as we know it. CO2, carbon dioxide. Here on Earth, it can be produced by geological processes. And it's a crucial fuel for plant life. When the results finally come in,
That big peak right there, that's all carbon dioxide. Yes. Yeah, that's beautiful.
We saw this giant carbon dioxide feature that just popped out right away in the data.
This carbon dioxide detection is just amazing.
We all had high fives. It was a big moment, but wow, we can look at the carbon chemistry of these planets in detail.
And it just brought a big smile to my face. I was like, yes, we did it.
There's some other bumps in there, right, that we don't like.
the spectrum also revealed a surprise. The first detection of sulfur dioxide on a planet outside our solar system. Sulfur dioxide is found in Earth's ozone layer, a crucial part of our atmosphere that shields us from the sun's harmful ultraviolet radiation. Finding these molecules in the atmosphere of WASP-39b is a landmark discovery.
What we've learned with JWST so far is that the data it's providing are exquisite for exoplanet atmospheres, and that has everybody salivating for more. More spectra, more hard transits.
The next big question. Can JWST detect an atmosphere on a much smaller, rocky, Earth-sized planet? One thing's for sure, it won't be easy.
We've never even detected an atmosphere around a rocky planet before. So now with JWST, we have our very, very first chance to do that on a very select few planets.
In a few months, they'll get their first look at a rocky world and see if they can detect an atmosphere.
Being able to perhaps make the first detections of an atmosphere on planets as small as the Earth is something that you only have dreamed of so far.
JWST is also looking for the chemical building blocks of life much closer to home, in our cosmic backyard.
One big question I want this telescope to answer is if there is life in our own solar system. If we found it in our own solar system, it would really hit home that it's not so rare that life can happen.
There are 3 places in our solar system, beyond the Earth and beyond Mars, which are good candidates to go look for life. And those are Europa, around Jupiter, and the moons of Saturn, Enceladus and Titan.
Titan is a really exciting moon because it has an atmosphere and rivers and streams and lakes and oceans, but instead of being made of water like they are on Earth, they're made of methane, like liquid methane. So it has like a water cycle like we have on Earth, but it's a methane cycle. And that's really exciting for scientists because if we find life on Titan, it's not going to be life like it is on Earth, it's going to be totally different life. So that's a really exciting thing to be looking for, but also how do you look for life that you don't understand? So it's also a massive challenge.
So the question comes up, can life evolve from chemistry in a liquid medium that's not water, that doesn't have the polar properties of water? And the answer is we don't know.
Researchers are also on the hunt for the ingredients for life as we know it on Enceladus, a moon of Saturn, and Europa, a moon of Jupiter.
Those are what are called ocean worlds, which means that they have liquid water in their interiors.
Imagine that there is a big body of water below the surface, protected from the environment.
Where there could be this subsurface ocean, where there could be hydrothermal vents, just like the ones that we have on Earth, which have life like plants and animals.
Full of organics, maybe some energy, internal energy, heat energy, and you have the soup of life. We don't know what could be happening there, but it's definitely a place that has all the right conditions for us to explore.
Some biochemists have suggested that it's in environments like this where life might have got going billions of years ago on the Earth.
That would be amazing to find. Even if we just found bacteria, that would be amazing.
Back in 2015, the Cassini mission studied Saturn, its rings and moons, and captured this image of plumes bursting out of the ice at Enceladus's southern pole.
We saw dozens of fine jets shooting off the South Pole of Enceladus. When these pictures hit the web exploded.
And so we see with Enceladus, there are places where the ocean actually escapes from the surface and it just flows out of these cracks and bursts out into outer space.
So this is, in effect, our best opportunity to study an extraterrestrial habitable zone.
The same may be true for Jupiter's moon, Europa, covered with cracks and ridges that could be caused by the heat of an ocean beneath its icy surface.
So we'll be looking for water signatures, so H2O, the same water that we have on Earth, and we'll also be looking for things like methane, which could be a chemical tracer that gives us an inclination that there might be something alive. Bacteria on Earth produces methane. We probably won't directly image life because you can't really image bacteria from a telescope, but you can look at what the bacteria creates.
while the team must wait several months for their observations to come in. JWST continues to send home stunning images, like this one of Jupiter.
You can see the rings, you can see the moons. I mean, this is amazing. And not only that, you can see those images, but you know you can actually explore those elements with incredible precision. You can see what they're made of, the composition, the ices, the molecules in them.
When I first saw the image, I didn't even think I was looking at Neptune. I thought I was looking at a totally different planet. Seeing the rings in that much detail was just mind-blowing.
The last time we had seen that complete ring system was more than 30 years ago when the Voyager 2 spacecraft had flown over Neptune. So what we are going to be doing is looking very carefully at the ring system today, looking at how that ring system may have evolved with time over those intervening decades, and trying to understand what that tells us about ring systems in general. How long do they last? What's driving them?
When you have a new telescope and you're just getting new data, it is very much like being, a child around the holidays, and you come downstairs and you're like, oh, what presents are going to be there? Every time you get this new image, it's just like unwrapping a present to basically see what there is to see. So it's a pretty exciting experience.
But before we get the chance to appreciate these mesmerizing images, they need to be tweaked.
The human eyes can only see a very narrow part of the spectrum, your blue to red, but there's light on either of the other sides of that spectrum. And of course, JWST is infrared, so it's on the red side of light.
Right, so Webb is an infrared telescope.
Oh
so
my
it's sensitive to
God.
light that is beyond what our eyes can see.
That's
So
gold.
that's 2 layers of adjustments.
It's
Oh
the
my
job of
God.
every
Look at
developer,
Look at
part
that.
science geek, part artist, to take this invisible infrared light and translate it into colors our eyes can see. JWST takes multiple
Crazy
images of a
tax.
celestial object with different infrared filters represented here in black and white.
We've taken light of different infrared wavelengths and split it up. So there's long wavelength infrared, medium wavelengths, a little bit shorter, and then shorter wavelengths.
Now, those infrared waves are translated into the colors of the rainbow.
We try to adhere to a philosophy of colorizing the data that we call chromatic ordering.
So we're capturing these wavelengths in infrared light, and we're shifting them into the visible part of the spectrum. And we are assigning colors that represent shorter to longer wavelengths, just like we would see them.
Think of it like a song played on a piano. Transposed, so we're hearing it in a different key, but it's still the same song.
So the longest wavelength is going to be red, so I will make that red. The next longest wavelength, I'll assign that green, and then the shortest wavelength, and that'll be blue. In this case, we actually have 4 filters. One of them is a narrowband filter that is really isolating a very specific kind of light, and that one we color orange. So after pulling everything together, I see the initial color composite image here, and it's really interesting. There's a lot of potential here, but I also see that it's very flat, and it needs some compositional work.
And then this where it kind of goes into the subjective. And
Oh my
where it's
God.
artistic.
The stars
Dogs!
are very different.
Get it.
Nebulas are very different. There isn't really like a hard point
Oh
where
my God, it's too cold.
going from science to art. It's sort of the whole process. The science
Crazy
is always there.
tax.
We're always respecting
I'm
the data.
crazy.
We're not trying to introduce things that weren't there in the data to begin with, and we're not trying to remove things that are there. So the whole goal of this is to create an aesthetically pleasing image that will capture someone's attention and hopefully inspire them to want to learn more about this region in space.
This image of the Tarantula Nebula is not only beautiful, JWST's infrared eye reveals thousands of baby stars once hidden from view, providing researchers new clues to decode the life cycle of stars.
You look at a newborn and you get a feeling for what that person will be when they are grown up. And the same thing for stars. You just measure them at the very beginning, you can imagine and you can infer how they will be and what they will become.
At the California Institute of Technology, an international team of scientists has gotten its data from JWST. They come together to discuss and debate what their test drive of the telescope has delivered.
You don't want to come in? Oh my God!
Europe, we have young people and old people.
Yeah, and I was gonna talk about, so this is I've known for many years in school days, and I would call it my family.
So for the last 2 years or so, it's been primarily meetings through Zoom, but there's no substitution for like just the energy you get having people in a room together. It's fantastic. And this is the Zoom.
The team is gathered to figure out what JWST is telling them about one of the most mysterious objects in the cosmos. Supermassive
All massive galaxies in the universe have a huge black hole at their center.
Because you wanna play.
What do I know about black holes?
Love to
So
play,
black
huh?
holes are just the most amazing
The gravity of a black hole is so extreme that whatever
Let's
it
see.
will never come out.
Not even light itself can escape.
Material is flowing into it the whole time. And then big bits of dust and gas and everything, which is swirling around the outside, all trying to fall into that hole.
But we don't know how they got there. We don't know how you make a supermassive black hole. We don't know how they formed. So when we're
Come
talking
here,
about
class.
massive black holes, versus galaxies, a big question is sort of who's in charge. You know, is the host galaxy in control of the galaxy's evolution? Or is that big black hole at the center? Is it having a really strong impact on how the galaxy changes over time?
In fact, there appears to be an uncanny connection between a supermassive black hole and the galaxy surrounding it.
Seems like the ratio of the black hole mass to the star mass is about 1 to 1,000. So that seems to imply that somehow the galaxy itself knows how massive the black hole is in it.
Doesn't make that much sense because the black hole, its sphere of influence is so small, it cannot really know what's around it. So how would those things be correlated? Why are they so correlated?
Keep in mind that we're talking about stars that are so far away from the black hole itself that the stars don't actually feel directly the gravitational influence of the black hole.
One of the best ways to investigate this strange relationship is to study merging galaxies.
When you throw two galaxies together, you can potentially grow a supermassive black hole. Feeding it, you're giving it all this material because it's crashed into this other galaxy. And by studying merging galaxies, we can potentially understand better how these supermassive black holes grow, what sort of interaction does the supermassive black hole have with its surroundings.
You have both black holes that are feeding and star formation happening in these galaxies.
All that activity stirs up so much dust, it's nearly impossible to see the action unfold.
It's very hard to actually look and see a black hole because all this dust and gas is in the way.
And here's where JWST's infrared eye comes into play.
So I went to grad school in Arizona, and every now and then a dust storm would go through. And anyone who's ever been in a dust storm knows you can't see through dust. But infrared light has this amazing property that it allows us to peer through dust.
This is an image taken by the Hubble Space Telescope in optical light of two galaxies in the process of merging. And this is what it looks like in infrared light with the Spitzer Space Telescope.
When you looked at it with Spitzer and infrared light, all of the energy was coming from that one region behind this shroud. And we knew we wanted to look at that.
They think somewhere inside this region is a feeding black hole. But while Spitzer was one of the most advanced infrared telescopes of its day, its yield was only about 3 feet in diameter. compared to Hubble's 8-foot mirror and JWST's massive 21-foot mirror.
And so clearly Spitzer, resolution is fairly low, but if you go now to what we see with the new James Webb images,
What
this is what we see when we have
Yeah.
a 6-meter telescope in space.
JWST's spectroscopes see through the dust, revealing these 3 distinct dots. 2 are clusters of star formation, and 1 of them is likely a feeding black hole.
So the climate scenario is that now see exactly what is under the giant blob.
We previously just knew that something was lighting up the dust. We didn't know what it was. We're now able to see, oh, there's a supermassive black hole there. And not only that, but it's destroying the dust in its immediate vicinity.
Give us a very close-up view of what's happening inside the galaxy. How the galaxy
You want to put tea, honey?
Yeah, a little bit, yeah.
The fact that we can see it in that level of detail is what it needs to be.
Hopes are high that in the coming years, this unprecedented level of detail will provide new clues to how this relationship between supermassive black holes and their galaxies took shape. It's early morning at the University of Texas at Austin, and this team has just received its data and images from JWST. Principal investigator Stephen Finkelstein keeps a video diary.
We definitely had some highs, like had some lows. It'll be exciting to see the data for the first time. This one looks really good. You guys,
The team is testing the telescope's ability to detect galaxies billions and billions of light years away. To answer a question that has puzzled astronomers for decades. How did the universe first turn on its lights?
When you think about the universe, it's sort of like we have this 13.8 billion year story. And we've put together a lot of the pieces of that story. We know a lot about it, but there's still these gaps in the story that we don't quite know the answers to. And one of the critical gaps is sort of the very first chapter of the story of the universe. You don't know
And I looked over my
gaps
shoulder, there's a gentleman sitting behind us, and he had this watch with like
If
a
the universe
leather
has
strap, and it looked like a wooden
This
face.
is its
And I just
earliest
said, oh
days.
wow, that's a really cool watch,
The
sir.
cosmic
And he said, thanks, and my son's
the afterglow of the Big Bang,
looks like wood,
when the
that's so
universe
cool.
is a
That reactor.
Let's go, let's go, let's go.
He and his wife crashed. And I was blown away by it. And I was just, it's just West Texas. It looks like, it just looks like a wood face on the watch. It's just like a little watch, but he just took it off and said it needs a new battery, and just gave it to my 9-year-old son. And now my son has his first real watch from some stranger at a monster truck show. It's just West Texas. It's just West Texas for him. With my son at the mouse.
A mysterious time known as the Cosmic Dark Ages.
Braden has
The Dark Ages was a period of the universe's history for several 100 million years when stars themselves didn't exist.
You can sort of think of it as a hydrogen fog, mostly hydrogen. And when you have just hydrogen atoms floating around, the intervening light would sort of bounce off the hydrogen. And so you can't see through it. So we sort of refer to it as a fog.
In our next picture, the universe is already in its adolescent years and pretty grown up. In fact, it's filled with galaxies.
We have, if you want teenage pictures and beyond, we're missing the color images.
Ah, my
We're
back.
missing that picture of how the Dark Ages ended and the first stars and galaxies took shape. A blank page in our understanding of our cosmic history. One that many researchers across the globe, like the Austin team, hope to fill. They spend a week scrutinizing analyzing their data in search of ancient galaxies.
So there were a group of us working here together, looking at these very distant galaxies. We all gather around the computer and look at them and say, yes, that's a good one. Yes, that's a good one. No, not that one.
In the process, they discover this faint, reddish blob.
Oh my God, I'm
At first
sorry,
I
though.
don't believe it. It's a redshift of 14. Redshift of 14 is about 290 million years after the Big Bang.
If correct, this date would mean that JWST's infrared eye is seeing further back in time than any telescope ever has.
One of the amazing things about telescopes is that they are literally time machines. They allow us to see the universe as it was in the distant past.
As light travels from ancient galaxies to our telescopes, it goes through a stunning transformation. From optical light, the light we can see, to infrared light.
What's happening in the universe is it's expanding, pulling space apart as it goes, and it's stretching the light in the same way.
This strange stretching is called redshift. The higher the redshift, the older the galaxy.
That's why the telescope was built, to find those distant, faint red galaxies, some of which are the first galaxies that formed after the Big Bang.
Now that's very neat. Obviously, right?
Based on their preliminary findings, the team thinks it might have found one of the oldest galaxies humans have ever set eyes on.
We've spent the last 24 hours trying to throw everything we can at this galaxy to convince ourselves that it is not an extremely distant galaxy, and we failed. So with that, it's my daughter's birthday. I'm gonna go take her to dinner and then spend all day tomorrow trying to write up this paper draft and hopefully get it out there pretty soon.
The team names the galaxy Maisie, after Stephen's 9-year-old daughter.
Feel like wasting time.
But finding Maisie isn't the biggest surprise.
We were able to see right away there were lots of really distant galaxies to find.
I don't know, like something, use
Every
my
time we did it
imagination
better,
or do
they just got
something.
more believable.
But, you know, it's true, I should, but there's nothing wrong with doing nothing sometimes. It's okay to do nothing.
In fact,
Whatever, you know, I work hard all the time. Oh,
ancient galaxies
it's nothing to do. You still
Yeah, I
outside?
know love. Why? No, it's
Oh, he's on the blanket, good.
Galaxies.
Yeah, but yeah, why should
It's about 100,000 galaxies.
Just a lazy day.
Hardly find any empty spaces in the images. Every tiny little speck, every space is a galaxy. And you zoom in and you see more. And you zoom in and you see more.
So this is Maisie's
Oh,
galaxy. This is red
yeah,
one,
that's-
right?
There's a lot of excitement, there's a lot of early
boring day,
preliminary
like
results
lazy day.
of the scientific process, where people
Yeah.
are finding
What?
candidates to be some of these
Lazy day, boring day. So what are you gonna do?
Go ahead, find the movie. I'm gonna go on
Where
a
you going?
bicycle. Hey!
because its age remains
Look at he's crazy. I should go for a
while
walk
the
with him.
telescope is still being
What tax? Come on,
It's
man.
really important to get the calibration of your telescope right, because when you take an image of a galaxy or a star, basically
Let's
the
go back to the
only thing that you're
Philippines.
measuring, the fundamental measurement is the brightness of that object
We're gonna-
at different wavelengths. And so you need to get that brightness right.
Same
which is
thing.
exactly what a
Bored.
team at the Space Telescope
City.
Science Institute is attempting to do. What they find will be crucial for the future of JWST and the reliability of all the findings produced from its data, including the age
Play the
of
guitar.
ancient galaxies like Maisie. The team is observing a cluster of stars known as Messier 92, one of the brightest and oldest collections of stars in the Milky Way.
These are stars that have been studied for decades by lots of telescopes everywhere. And we know a lot
It is.
about them.
But when they
Still
get their
loose.
data from
This one's
JWST,
still loose. I thought I could tighten them all.
something's not adding up.
When we were looking at data for the first time, what we were seeing was that the brightness of stars measured on the different detectors.
Ja.
So one detector was measuring the star a little bit brighter, the other one was measuring it a little bit fainter.
Wanna type? Wanna typing?
Astrophysicist
Ah!
Hakeem O'Shea
Stop.
demonstrates the discrepancy they found
see, maybe.
Assume that this place
Let's see.
is a star that has been measured over and over and over again for decades. And I know how bright it is, really. And now I have a detector that I'm gonna point at it. And it's
Get your
gonna give
toys.
me a reading for how bright this
Lex,
light is.
get your toys. You wanna play?
So I
You wanna
point this
play
at
with
my
your toys?
and I lock
Go
in the
get
measure value.
Come
Now I'm gonna take the next detector. I'm gonna do the same
your
thing.
toys. Come on. Get your toys.
And I do that with another
Where
detector.
are your toys?
And lock in the value. Well, guess what? They don't all have the same reading. They
Where
are
are your
slightly
toys?
different, one from the other, and that's normal. If I took the light from a single star and shined it on different detectors, they may each give us a different reading.
It's a common problem instrument scientist Mike Ressler knows all too well. He helped to develop the detectors for one of the instruments on board JWST called MIRA.
The detectors we use in Miri are silicon detectors. They are very similar to the detectors in point finders in the Google camera.
In fact, if you take off the lens, you'll find a detector behind the shutter. This greenish gray rectangular silicon chip.
The light comes through the lens and gets
There's a lady
and that is the
John
each detector
all
has its own
listens is gold, and she's buying the stairway to heaven.
On board JWST,
When she gets
each with its
down,
own personality.
if the stars are all closed, in a world she can get what she came from.
Using the known brightness of the stars in Messier 92 as their guide, the team adjusts how it processes the data, updating the calibration of the telescope.
Once we calibrate our instrument, we can go and point at things that we have no idea how bright they are. And by measuring its brightness, we can now get a very accurate measurement of its distance. And those are the numbers that go into our calculations of the element.
Back in Austin, the team is also improving how they process their data. This, along with tweaks in the calibration of the instruments, modifies the
Yes. Oh yeah, Wonderstruck. Good show, love.
The larvae of lake fly midges hide out away from predators.
Look at him, look at him.
In the rainy season,
It's an amazing world.
to the surface and undergo a magical transformation.
Scared in
Look at that.
thunder.
No, look.
At dawn, the first adult midges start to break out.
What? Butterfly? Ano? Yeah.
No.
Dragonfly.
Millions upon millions of newly hatched lake flies are taking
They're flies. Look at them. There's so many flies that there's a cloud. Oh my God.
Yeah.
Those are flies. That looks like a cloud.
Yeah, it's clouds.
No, that's flies.
Why?
Millions and millions and millions of
The
flies.
one, the white?
Yeah. Look at it.
That's fake.
That's not fake. That's real. Those are actually, there's so many millions coming out of the water.
They will all drop to the water surface, release their eggs, and die.
Look at that. I'm not kidding you. Those are actually clouds of flies. Those are clouds. See the real clouds?
Yeah.
Malawi may look like an inland sea, but it's dwarfed by the world's largest lake, Baikal, in eastern Siberia.
It's the world's biggest lake.
Where is that?
Siberia,
Like
like Russia.
Ah, yeah.
Very far.
400 miles long and over a mile deep, Baikal contains 1/5 of all the fresh water found in our planet's lakes and rivers.
Oh my God, that's amazing. 1/5 of all the water is in that
It's sealed
lake.
by an ice sheet over a meter thick.
Oh my God, they went under there.
Baikal is the oldest lake in the world, and
You were just in the bed. Go back to the bed. Go to bed.
in isolation.
Go to bed.
80% of
Go to
its
bed.
species are
Go to
found
bed.
nowhere else on
Go to
Earth,
bed.
including
Now you go to bed. Good boy. No, he wants some love.
With this seal and its marine-like forests of sponges, Baikal seems more like a
Look at that.
lake than a lake.
Get your toys. Get your toys. Go. Get your toys. Get your toys. Go. Get your toys. It's no play without toys. Yeah.
Look at that thing, love.
What is that? Ah!
It's
Like
like
shrimp.
it's like a shrimp.
Yeah, it's
It's like a shrimp.
wow, look at that. Cute.
That's what we eat all the time.
Ah.
Are the key scavengers in this lake. The water here is just too cold for the bacteria that
Lobster.
That's freezing cold water.
Hey. You're jumping on me?
The males held court in a unique way. They pick up rocks and hedgehogs and fall to their attending females. Successful displays lead to mating.
Alright, everybody, choose any of these for just $6.
Can you get a day single with a 10-piece knot?
Yeah. How about 2-day singles for $6?
And that's class.
Sorry.
Choose wisely. Choose Wendy's 2 for $6. Music like you fight your worst nighttime symptoms, so you can get to sleep and wake up ready to go. Clean.
Dr. Big.
Wake up to a new year with Mucinex Night. It's not cold in the new season. It's always comeback season. The Mercedes-Benz 3-point Star was designed to symbolize the environments we travel.
We'll get your
Today,
toys.
we ignite the elements that are always there. As every action counts, we are committed to building a 40% recycled materials. Repurposing waste such as old fishing nets. Going all electric by 2030. Land, sea, air. Join us on our journey to a more sustainable future.
I love your browser history.
You are so generous.
NordVPN, safely be you.
With one of the best savings rates in America, banking with Capital One is the easiest decision in the history of decisions. Even easier than this.
Stop. You're in.
Oh, cool. Yep, even easier than that. What's in your wallet?
I'm a screen addicted tween, and if I'm not posted on social media, I don't feel seen. Oh my God, Mom, you gotta
No, keeping my eyes on the road is paying off with DriveWise.
Did DriveWise from Wall State save for avoiding mayhem, like me.
Oh, movie.
Only pay for what you need.
Worked hard at hour one. It's twice as hard. You take it again the next day. So Betty can be the
Get your toys.
Let's be more.
Where's your toys?
Seize the day.
Go get your toys. Oh,
Thank you. So expensive. So why is Omar sleeping like a baby? Because he made the smart choice to shop with IKEA. And he has to stop dancing since she's with IKEA, you're caring for your wallet. And you can and your dad.
it's my. Oh my God, my legs. That's nice. Where is it? Go here. Go here. Get the toys. Get the toys. Get the toys. Get the toys.
Turn this down for a second.
Get the toys. Get the toys. Get the toys. Go get the toys. Come on, buddy. Go get the toys.
That was nice. Jeannie said that about. She said when you first came here, she didn't know how old you were. Maybe 20.
God.
That makes me feel like they must have been like, "What's wrong with Pete? He's bringing a young woman like Skip, you know." Oh my God, love, what? Don't tell me I'm on the internet. Oh my God, love, that's not good. I don't even know. Love, geez. You gotta be super careful with that. That's not right. It's not right, love. You have to at least tell me.
Your mouth.
I know, but I thought we had privacy. You know? It scares me. I don't want to hurt anybody's feelings. I don't want to. That would be so devastated. You have to warn me. You have to give me a warning.